How's everybody doing? The the emphasis for the final really is on the second half of the course. There is pre-midterm material on it, and of course you need to know the pre-midterm material to be able to do the second half, but we're mostly focusing on the second half. While we wait for other people to come in, let's have one more song from the Cowboy Fringant. I'll go check the email to make sure nobody's having any difficulties accessing this. I'll be right back. Questions while we wait? right, welcome everyone. If you're fast, you can probably do the exam in 2 hours. If you know what you're doing and there's no hesitation, the Dalton is asking if half of the long answer questions will be proved like the midterm. Seems reasonable to think so, yeah. Before we start, I wanted to point something out to you that you might not have noticed. Linear independence is equivalent to what I like to refer to as the unique representation property, in the sense that if you have a set which is linearly independent and it represents, and you can represent a vector as a linear combination of these elements, right? So observe. So if you've got a set V1, V2, all the way to Vn that is linearly independent, and you can represent an element as a linear combination of these vectors, then that representation is unique. There's only one way to represent V, and it's using A1, A2, A3, and so on, AN. There's only one way. And let's observe why that's true. Suppose there were two ways. Right? Suppose it's also B1, V1 plus B2, V2, and so on, all the way to Vn, Vn. Then you have these two things equal to each other, so bring it over to the other side. Right? This is equivalent, so if and only if A1 minus B1, V1. So, right, I mean, I'm bringing the B's to this side and factoring out B1, V1 and V2 and so on. So then you have a linear combination equal to 0. And since the VI's are linearly independent, the only way that happens is if A1 minus B1 is equal to 0. And A2 minus B2 is equal to 0. And so on and so on. In other words, if A1 is B1 and A2 is B2, and so on all the way to AN is Bn. So a very nice observation here. In other words, if you can express an element in terms of a linearly independent set, there's only one way you can do it. And in particular, if you've got a basis which is linearly independent and spans the vector space, then every vector can be written as a linear combination of your basis elements, and that way of writing your vector is unique. So every vector is a unique linear combination of elements in the basis. Why don't we take an example to illustrate? I claim that this set is a basis of R2. Dalton is asking what is V in this case. V is just some basis. It's just some vector. So I'm suggesting if you can express a vector as a linear combination of the VI's, then there's only one way this can be done. In other words, the representation is unique. The linear combination is unique. If you can express it one way and you can express it another way, it turns out that the coefficients have to be the same. So there was only one way to express it to begin with. Let's take an example. I claim that this is a basis. You can prove it. Let's not prove it. Let's just assume that it is. But, I mean, the proof is easy. This is the basis for R2, right? I mean, R2, you know, has dimension 2, so every basis should have 2 elements in there. And, well, you can do the rest. So this basis for R2, and let's express minus 1, 2 as a linear combination of these basis elements. Right, what do we want to do? We want A times the first one plus B times the second one to be equal to minus 1, 2. So if you rewrite this left-hand side, this is A plus B and A plus 2B. And if these two vectors are the same, then their components must be the same. So A plus B is minus 1 and A plus 2B is 2. You can set up a matrix if you wish to solve this, or, you know, whatever you want to do. Maybe from the first one, A is minus 1 minus B. Plug that into here, and you get minus 1 minus B. So that B is easily seen to be 3. And if B is 3, then A is minus 4. Does that work? 4 minus 3 is, no. Minus 4 plus 3 is minus 1. And minus 4 plus 6 is 2. Looking good. There it is. Right? So what are we saying? We're saying that minus 1, 2 is minus 4 times the first basis element plus 3 times the second and by our previous observation, this is the only way to write the vector minus 1, 2. Because these form a basis and are consequently linearly independent, and thus they had this unique representation property. Why don't we, while we're here, for fun, let us repeat this process with the vector 1, 0, right? Let's write 1, 0 as a linear combination of these elements. And, you know, let's be smart here. If I want to get rid of the second component here, I want a 0. So if I do 2 times this, if I do 2 times 1, 1, minus the 1, 2. I get rid of the 2's. So that's what I want. And then in the first component, it's 2 minus 1, which is 1, exactly what I wanted as well. If it had been something else, I could have divided the whole thing. But we see that it works. And once again, this is the only way to write 1, 0. So we've stumbled upon it, and turns out it's the only way. And while we're here, observe that if we added those two together, we get the vector 0, 2. And if we add those two together, right, because we're adding the left-hand sides, let's add the right-hand sides. And it's minus 4 times this vector plus 2 times that vector. So we're going to get a minus 2 times that vector. And here 3 minus 1 is 2 of those. And once again, well, I mean, let's verify our answer here. Minus 2 plus 2 is 0. Minus 2 plus 4 is 2. So it works. And that was the only way to write it, again, by this unique representation property. Now, let's talk about what we really want to talk about. Representations in different bases. And you know that matrices is all about being as efficient as you can. And here, right, what are we doing when we're representing an element in another basis as a sum or as a linear combination of elements in a different basis? Let's try to be as efficient as we can. All that's important, right? I mean, as we saw here, when we're adding these two things, we're really just adding the coefficients of each of the vectors. Good, nice to see you. So we're really just adding the coefficients of each of the basis elements. So let's introduce a notation, right? I mean, very much like the matrix, when we set up a matrix, we removed the x's, the y's, and the z's, right? And we said we were going to reserve the first column for the x's, second column for the y's, third column for the z's, that kind of thing. Let's do the same thing in this case. Given a basis where the order matters, consider this vector, which is -4 times the first basis element plus 3 times the second basis element. Let's give this a name. Let's call this basis B, right? So -4 times the first basis element plus 3 times the second. Let me introduce notation. Again, because all that's important is the coefficient multiplying each of the vectors. -4 times the first plus 3 times the second in your basis B. Similarly, this vector, the vector 1, 0, is 2 times the first basis element minus 1 times the second. This vector, or this linear combination, is 2 times the first basis element plus minus 1 times the second basis element of the basis B. And when you added those together, what happened? You got a vector which was minus 2 times the first basis element plus 2 times the second. Exactly. Minus 4 plus 2 is minus 2. 3 minus 1 is 2. Exactly as it should be. Exactly, right? It's exactly like matrices, where you would reserve the first column for the x's, the second column for the y's, and so on. Here, the first entry is what is multiplying your first basis element. The second entry is what is multiplying your second basis element, and you're adding those together. Because really, all we're interested in are the coefficients anyways. What would be a reason for changing the basis? An excellent question. Let's hold off on that. And let's first get acquainted with this change of basis business, and then we'll see why that may be desirable. So what are we saying? We're saying that the vector minus 1, 2 that you're used to working with, or rather we should say the vector minus 1, 2 in the standard basis is equal to negative 4, 3 in the basis B. Similarly, the vector 1, 0 is the vector 2 minus 1 in the basis B. The vector 0, 2 is the vector minus 2, 2 in the basis B. You understand that these are representations for exactly the same thing. Let's introduce a definition. An ordered basis is a basis B where the order of the elements is fixed. And unchanging. Right? So the order is fixed and unchanging. In other words, this basis, this ordered basis, 1, 1, 1, 2, is not the same as the ordered basis where this one comes first and that one comes second, right? The order matters very much. So an ordered basis must be a basis, so it has to be linearly independent and spanned, but also the order matters very much. So whichever vector comes first, whichever vector comes second, and so on, you can't change those around. For a fixed ordered basis, that's the order of your basis, and it matters. We introduce a notation. For a V, which is a linear combination of those elements in the standard base, in the ordered basis, right? If you can write V as a linear combination, then this is A1 times the first one, plus A2 times the second, and so on. A1 times the first one, plus A2 times the second, and so on, all the way to AN plus AN times the length. So exactly what we did before, right? Minus 4 times the first basis element plus 3 times the second, we're doing this. What's an example of a basis that isn't ordered? Well, I mean, as soon as you write it down, it is ordered, right? But the point is, this basis is actually the same as this basis if you view them as sets, right? Because two sets are equal if they have the same elements. So every element in here is an element in there and vice versa. So these two sets are equal as sets or as bases, but not as ordered bases, right? Because the order is different. In fact, if you look at this element, right, minus 4, 3 in the basis B, right, because it's minus 4 times the first one, plus 3 times the second one in the basis B. If you look at it in the basis B prime, it's actually 3 times the first one, minus 4 times the second. So it's actually the element 3 minus 4 in the basis B prime. So it's like permutations versus combinations. Exactly. Exactly. In combinations, the order doesn't matter. In permutations, the order does. And that's exactly what's happening here. There are no underlying properties, only the order. Just the order matters. How do you prove the span of a non-standard basis? From the definition, right? I mean, here we show that this element was a linear combination of those two elements. If you want to show, I mean, here I just stated that it was a basis, but you really should prove it. You should prove span and linear independence. Since Dana is asking, let's take a moment to prove span. So the claim was that B was a basis of R2. Let's prove span, and I'll let you prove linear independence. To prove span, you take a vector in R2. And the question is, can you write it as a linear combination of these elements? So if you take a vector in R2, V has the form xy. Can you write it as a linear combination of elements in your basis? Is there always a solution for A and B? Well, if you rewrite this properly, this is A plus B and A plus 2B. So we have A plus B is equal to X and A plus 2B is equal to Y. Again, the question is there a solution? Let's write this in a matrix. 1, 1x, 1, 2y. Or you could have rewritten this as 1, 1, 1, 2, AB is equal to XY. Let's do that instead. I mean, you could do this. You could row reduce and solve. But let's do it this way. It's going to be a bit quicker. This is A times the vector AB is equal to XY. And you can solve if A is invertible. But A, which is the vector the matrix, which is this matrix, is invertible. And its inverse, determinant is 1. So 1 over the determinant. 2 minus 1 minus 1, 1. So AB, which is A inverse XY, and there you have it, you've solved. You've solved for A and B. There's always a solution. This proves span. Jean-Pierre was asking, are vectors from the new basis somehow related to the old ones? It's an excellent question, and we'll see how they are related momentarily. Does it mean that 2 by 2 matrices can be mapped into complex numbers? Well, I mean, short answer, there you can map. There is something that can be done. There's something that can be done. But if you're just asking for a map from M22 to the complex numbers, I mean, there are many maps. Because in fact, the real numbers are themselves complex numbers. So you could map M22 to the reals, and that's fine. In fact, there are linear transformations which do that. But there are other maps that are not linear transformations. So that's a short answer. What I think you might have wanted to say is R22 to C, but let's not even get into that. Do linear transformation matrices need to be transformed to new basis? That's exactly where we're going, George. We'll see that in a moment. To show span, is it enough to state that any set of n elements spans a vector space of dimension n? That is not true. Lily, that is not true in general. Just because you have n, so long as the elements are, okay, sorry, I hadn't finished reading your question. I should have read it till the end. So as Lily points out, if you're dealing with a vector space of dimension n, you know that a set of n vectors spans if and only if it is linearly independent. And you get a flavor for why that's true right here. Here we're proving span, and in linear independence, x and y are 0. And you're asking the question, is 0 the only solution? Well, it is if your matrix is invertible again. So span if and only if linear independence. So to answer Lily's question, you can use that. You can use that result. You can use that result if you know the dimension of the set of the vector space you're working with. we were talking about representations in different bases, and let me introduce the term standard, ST, meaning we are in the standard basis, the usual basis we like to work with. Let's take an example. Consider the basis 3, 1, minus 1, 1. Again, this is a basis for R2. Let us express the standard basis elements in the basis, in the ordered basis B. Right, so let's express these basis elements. Let's express the vector 1, 0 and the vector 0, 1. In other words, the elements of these standard basis as linear combinations of these basis elements. Can we cheat without doing too much work? I mean, of course, A times the first one plus B times the second one is equal to that, and solve for AB. Right, that's the usual way to do it. Let's cheat here and observe. What do you want to do? You want to get rid of this second component. Right, so if you do 3, 1 minus 1, 1, the second component becomes a 0. Is it what we want? What do we get if we do that? We get the vector. Does everybody see it? This is the vector. There's a little lag here. 4, 0. Thank you, George. This is the vector 4, 0. Right? You can really read it off. Jonah, thank you. You can read it off. And now we want the vector 1, 0. What are you going to do? Multiply both sides by 1/4. And so we get 1, 0 as 1/4 the vector 3, 1 minus 1/4 the vector minus 1, 1. Very nice. Absolutely. And consequently, the vector 1, 0, which was in your standard basis, is now the vector 1/4 minus 1/4 in your ordered basis B. Right? 1/4 times the first basis element minus 1/4 times the second. Convinced? Similarly, for 0, 1, can we write it as A times the first basis element plus B times the second? Well, I mean, let's well, I mean that's really the question, and you can solve for A and B. Let's not do that. We already know that this is the vector 1, 0. So if you add it to that, right? Minus 1, 1 plus 1, 0 gives you the vector you want. And this, no, this rather, we just found. So that was 1/4, 3, 1, minus 1/4, minus 1, 1. So it's 1/4, 3, 1. And 1 minus 1/4 is 3/4. Minus 1, 1. So in other words, it's 1/4 times the first one plus 3/4 times the second one. Very nice. Very nice, Andrea. Exactly. Exactly the answer we got. Right? Again, by the unique representation property, we found a way. It is the only way. Any other answers to that? An excellent question, Franco, right? And the answer is no. There's no other way, because we saw that linear independence was equivalent to this unique representation property. If you solve for A and B, you're going to get the same answer. Questions? And so, I mean, really, what are we doing here? Right? I mean, now that you have the vector 1, 0, and 0, 1, then any other vector, let's say the vector 2, 3 in the standard, is, of course, 2 times the vector 1, 0 plus 3 times the vector 0, 1. But you just found what the vector 1, 0 was. So this is going to be 2 times the vector 1, 0 was the vector 1/4 minus 1/4. And the vector 0, 1 was the vector 1/4, 3/4. So this vector is that, which is 1/2 minus 1/2 plus 3/4, 9/4. And this is going to be 5/4 and 7. Is that right? 7/4. Right, now that we have the standard basis, we can represent any element as a, thank you, Jonah, as a linear combination of the first and second basis elements of B. Franco, I'm not sure what you mean there, but my claim is that if you try to write the vector 0, 1 as a linear combination, much like we did here, A would have to be 1/4 and B would have to be 3/4. Yeah, essentially. I claim that A would have to be 1/4 and B would have to be 3/4. Now so really what are we doing? We are rewriting an element Jean-Pierre, you'll be redoing this in Math 223. So it's a good idea to learn it now. 2-3 was just an example, And what are we doing? We're taking an element in the standard basis and we're rewriting it in the basis B. We're changing the basis, right? This element, this vector 2-3 that you're familiar with, is equal to the vector 5/4 and 7/4 in the basis B. Math 223 is, what is it called? Advanced linear algebra or something? Or I don't know. I forget its name, but it's the second linear algebra course. Right? So we're rewriting a vector just in a different form. We're changing the basis. Claim a change of basis is a linear transformation. Change of basis is a linear transformation, right? If you take two vectors and you write them in terms of another basis, well, I mean, right? This vector can be viewed as the sum of two vectors. Break up those two vectors in the basis, rearrange them. There's only one way to write it. This way works, and consequently, it's the only way. A change of basis is a linear transformation. You have two vectors. You can find the change of basis for one vector, find the change of basis for the other, and add them to get the change of basis for the original sum. Same with a, right? And so, I mean, let me prove this completely. Are all linear transformation a change of basis? No. Well, actually, that might have been, no. It's a valid question, but the answer is no. The answer is no, because we'll see that a change of basis, you're going from one basis to another, so it has to be invertible. Has to be an invertible. The zero matrix, exactly, is an easy counterexample. But the point is that this is actually an invertible linear transformation. You can go from one to the other and vice versa, right? Let's prove this. Change of basis is a linear transformation. If you have an ordered basis, so let B be an ordered basis. If you take U and V in your underlying vector space, U can be written as A1, V1, AN, VN, and V can be written as B1, V1. In other words, a linear combination of your basis elements. then u plus v can be written a1 plus b1 v1, and so on. This works, and by the unique representation property that we saw in the beginning, it's the only way to write it. But this is the representation a1, a2, an in the basis, in the order basis b, and this is b1, b2, bn in the basis b, and consequently this is a1 plus b1, a2 plus b2, in your basis b. So the sum of the representations is a representation of the sum. So that proves the u plus v business. And now I'll let you do the scalar multiplication. But it's exactly the same thing. Right? I mean, maybe I should make it clear here. Here you're taking a linear transformation from a vector space V to a vector space V, where T of U, which is T of A1, V1, is really the vector A1, A2. Right, so T of U is this, T of V is the same thing, and T of U plus V, as we saw, is just A1 plus B1, AN plus BN, but it's this plus this. Which is T of U plus T of V. Jean-Pierre is asking, does the change of basis modify the vector space? It does not. Still the same vector space. Still the same vector space. Still with the same addition and multiplication. It's just that you're dealing with a different basis. And that's exactly what George was saying as well. It keeps the same algebraic properties. Absolutely. Now, where are we going with this? We were looking at linear transformations, of which change of basis is a linear transformation, of which change of basis is an example. So the linear transformation is equal to the basis. Well, that's not a proper statement. What should we say? What should we say? The linear transformation is a change of basis. Right? All I'm doing is I'm rewriting U in a different basis. So it's almost like an identity. It's sending U to U, but a different representation for U. Right? I mean, we had seen an example. I've rubbed them off now, but I think we had the basis 3, 1, the ordered basis 3, 1, and 1 minus 1, if I remember correctly. And so here, the change of basis is a linear transformation going from R2 to R2, and it's just rewriting the vector 3, 1 in the basis B. Minus 1, 1, George, thank you. So I'm going to make a difference because I'm just going to look at this vector element. So our transformation here sends the vector 3, 1 to the vector 1, 0 in B. Right? Because this means 1 times the first basis element plus 0 times the second, which is the vector 3, 1 in the standard basis. So it's just rewriting the elements from standard to the basis B. Similarly, your transformation would send minus 1, 1 to the vector 0, 1 in B. And so on, right? Maybe if we add the 2 here, it would send the vector 2, 2 to the vector, to this sum, which is the vector 1, 1. Does this mean we can rotate a vector space? I don't know about rotating a vector space. What would that mean? Because the vector space has would you rotate every element in the vector space? And that makes sense maybe if you're in R2, you might rotate, that's fine, or R3 or Rn, rotate about something that's fixed. But what about rotating polynomials? Unless you mean rotate in a basis, that would be interesting as well, right? Like a permutation of basis, as somebody was suggesting earlier. But let's not, where I think we're moving away, and I will still have a lot of material I want to cover. So let's move on from that. We were looking at linear transformations, and we saw that multiplication by an n by n matrix, or an n by, multiplication by an m by n matrix if A is m by n, multiplication by an m by n matrix can be seen as a linear transformation from Rn to Rm, right? It takes vectors in Rn and spits out vectors in Rm. Right, this is m by n. So if you take a vector, which is a something by 1, it has to be n. And the answer, viewed as matrix multiplication, is m by 1, so a vector in Rm. In other words, multiplication by a matrix is a linear transformation. But we also saw in class that every linear transformation from Rn to Rm may be viewed as multiplication by a matrix. And that was a very beautiful observation. I shouldn't say similarly, but conversely, every linear transformation from Rn to Rm is multiplication by a matrix. And let's illustrate with an example. Consider this linear transformation. I won't prove that it's a linear transformation. I'll leave that to you. In the interest of time, but you can show that easily. Show this is a linear transformation. We saw in class that if you know how linear transformation behaves on a basis, you know everything about that linear transformation. And in fact, we saw how to get the matrix representation by observing how T behaves on the standard basis. T of 1, 0, by definition, assuming now that we have shown it was a linear transformation, which you can do on your own, T of 1, 0 is minus 2, 1, thank you. And T of 0, 1 is 1 minus 2, thank you. And so the matrix representation where A is the matrix made up of these as columns. And let's understand why that is. Exactly, as Jean-Pierre mentions, in general, maps are not linear transformations, right? So linear transformations have important properties, namely the transformation of a sum is the sum of the transformations. The linear transformation of C times a vector, you can pull the C out, right? Those are the conditions for being linear. So in general, if you write down an arbitrary map, right, as soon as you introduce squares, cubes, exponentials, stuff like that, you're in trouble. Products, x, y, these things are not linear. They're not going to be linear transformations. Let's convince ourselves that our linear transformation is multiplication by this vector, by this matrix rather. Minus 2, 1, 1 minus 2. What happens when you multiply this matrix by the vector xy? Well, you get 2x plus y minus 2x plus y and x minus 2y, exactly your linear transformation. So your linear transformation really is multiplication by this matrix. The matrix we got by looking at how T acts on the standard basis. let's go back to the change of basis. We argued that the change of basis was a linear transformation. So it should have a matrix representation. Well, it is asking, how do we find matrix for a linear transformation, such as projection on a specific line or reflection? Short answer, if you know how it acts on the standard basis, put those as columns, and there's your matrix representation. We'll see a shortcut in a moment, though. And by moment, I mean half an hour if all goes well. So linear transformation is only with addition and subtraction and scalar multiplication, essentially, Franco. Absolutely. Yeah, MJ, thank you. So we said change of basis was a linear transformation, so it should have a matrix representation. Let's illustrate with an example. Consider the ordered basis 3, 1, minus 1, 1. How to project on a line using linear transformation. Don't well, let's quickly answer George's question here. What we're saying is that T of V, so fix a vector W on which you're going to project. If you're projecting on the line, it's essentially projecting on the direction vector. So W is going to be your direction vector. But in general, if you fix a vector W, the projection of V onto W is a linear transformation. That's it. There's your linear transformation. If you wanted to do a bit more, you know that this is V dot W over length of W squared times W. So now here's your, again, another way to rewrite your linear transformation, and then you can show that it's linear. The dot product of a sum is the sum of the dot products. And when you C times a vector, you can pull it out. And then do that on the standard basis, and you get the matrix. Exactly that. Exactly that. But we'll see another beautiful observation in a moment, because I'll come back to this example. But before we do that, let's talk about the linear transformation. Let's talk about the matrix representation for this basis, for the change of basis. If you put these basis elements as columns, what does that give you? What do you get? Well, you get this matrix. What is that matrix? Observe that if you multiply by the vector 1, 0, what do you get? You get the vector 3, 1. So multiplying by the vector 1, 0 gives you the vector 3, 1. But the vector 3, 1 is the first element in your basis. So if you treat this as 0, 1 in the basis B, meaning the first basis element, it gives it to you in the standard basis. Similarly, when you do this multiplication, you get the vector minus 1, 1. The second basis element in your ordered basis. But this is your second basis element in the ordered basis. So it rewrites this in the standard basis. So this matrix takes elements in the standard basis, takes elements in the basis B and rewrites them in the standard basis. Let's introduce notation for that. A change of basis matrix from an ordered basis to another ordered basis let me not use B, let me use C. It is denoted by P. You're going from the basis B to the basis C. Is this a linear transformation, taking elements from B to standard? It is, exactly. That's exactly what it does. So it's a change of basis from the basis B to the standard. So if we're adopting this notation here, if this is B, then the matrix 3, 1 minus 1, 1, in other words, rewriting these as columns, takes elements in the basis B and rewrites them in the standard basis. right? So now MJ was, right, yeah, there it is. So, yeah. So MJ is viewing it as an actual linear transformation. That's fine. That's fine. That's fine. But let's view it as multiplication by a matrix, namely this matrix. And now it's easy to understand that it takes elements in the order basis, B, and spits them out in the standard. Exactly, Terry, right? 0, 1, B means 0 times the first element plus 1 times the second, 0 times the first, 0 times this, plus 1 times that. So it just gives you this, which is that. So 0, 1b is the same as minus 1, 1 in the standard. How are we doing? So now, let's go back. Well, before we go back, imagine you wanted to do the opposite. Andre is asking if we can change the notation. Let's not. Let's not, because everybody uses this notation. Well, I mean, by everybody, I thought it was notation that was lost, but apparently a lot of people are still using it. So the recording will be uploaded absolutely to my courses. So let's not try to adopt any new notation, and let's stick with that one. What I want to suggest is, what if you wanted to do the opposite? What if you wanted what about the opposite? A change of basis from C to B. In that case, you'd just be doing the opposite of what you were doing before. And that is, so the opposite or the inverse operation. That is the inverse of B to C. So the inverse matrix, exactly that. So now, let's ask the question. Well, I mean, maybe we want to convince ourselves. Shall we convince ourselves? With P going from B to the standard, which was 3, 1, minus 1, 1. The inverse what is the inverse? This has determinant 4, so 1 over 4. 1, 1, minus 1, 3. Is that correct? That's 4, and that's 0, 0, and 4. Looking good. Looking good. And what does that do? This sends the vector, it should be going from standard to the basis. So if I took the vector 3, 1 What does it send that to? It sends that to 4 divided by 4 is 1, and minus 3 plus 3 is 0. So it sends this to that, and sends the second basis element to minus 1 plus 1 is 0. 1 plus 3 is 4 divided by 4 is 1. There you go. It sends this to that, which is, if you think of this as 1, 0 and the base is b, it really is the vector 3, 1. And 0, 1 in the base is b. The second one is minus 1, 1. We can recognize the values from earlier. Yeah, exactly, right? Very nice, MJ. I rubbed everything off, and it wasn't clear, but if you have the work in front of you, then you recognize it as being exactly what you want. So this is the change of basis from standard to B. Very nice. Very nice. Right, so let me point out this is a very nice and elegant way to rewrite elements in one basis versus another. Should there be a fine, certainly, right? This is in ST. Oftentimes, if nothing is mentioned, it's understood to be standard, right? In the same way as with logarithms, when there's nothing, it's understood to be base 10. But for completeness, let's write it nonetheless. So let's go back to our linear transformation. And we saw that we could get a matrix representation for T by looking at how T acts on 1, 0. So that is minus 2, 1. And how T acts on 0, 1, the standard basis elements. And so T is really multiplication by the matrix. And everything worked. Well, here's my question. What if you took the ordered basis B instead? What if you took the ordered basis B instead and looked at how T acts on this ordered basis? If you look at how T acts on the vector 3, 1, what is T of 3, 1? Work it out, you tell me. Same T of 3, 1. Who has it? Nobody? Minus 5, 1, thank you. and t of minus 1, 1. Three minus 3, thank you. 3 minus 3. And what if you used these as columns of your matrix representation? Right? Like we did with the standard basis. T of 1, 0 was this. T of 0, 1 is that. We use those to build a matrix representation. If you know how T behaves on a basis, you know everything about your linear transformation. This is a basis. We know how T behaves on that. We know everything about the matrix, about the linear transformation. But what is this? What is this business? Well, let's investigate what that is. What happens if you multiply this by the vector 1, 0? You get the vector minus 5, minus 5, 1. Right? If 1, 0 is viewed as 1 times the first basis element plus 0 times the second, and similarly, this gives us 3 minus 3. 3 minus 3. So if this is viewed as 0 times the first basis element plus 1 times the second, this representation is a representation for T which takes elements in the basis B, acts on it as T would, and spits out the answer in the basis, in the standard basis. So it takes elements in the basis B, acts on it, and spits out the answer in the standard basis. How are we doing? Let's take this a step further. We saw a change of basis matrix from the basis B to the standard, which I believe was 3, 1 minus 1, 1. Is that right? It takes the vector 0, 1 and gives back the vector 3, 1. So it takes elements in the basis B and spits out their equivalent in the standard basis. Right? So this is a transformation from B to standard. So the inverse is the transformation from standard to B. And it's the inverse of that, which we had calculated to be 1/4, 1, 1, minus 1, 3. And now, imagine that you have an element in the standard basis. If you rewrite it in the basis B, still the same element, it's just rewritten differently. You're going to act on it by T, which takes elements in B and spits out the standard, spits out the answer in standard form. And this should be the same as T acting on standard basis elements and spitting out the answer in standard basis elements. Let's see if that's true. This is that. This is that. Let me pull the 1/4 out. So -5 minus 3 is -8. -5 plus 9 is 4. 1 plus 3 is 4. And 1 minus 9 is -8. And this is -2, 1, 1, -2. Exactly the matrix representation we had for the original. The original matrix representation. In general, well, let me give you a moment to digest this. Questions here? So the matrix T is doing two things exactly. It's acting on it. It's acting on vectors. In this case, it's taking vectors in a basis B, acting on it. I've rubbed it off now, but acting on it as the linear transformation does, and spitting out the answer in the standard basis. In general, if you have imagine a linear transformation acting on basis elements that are in B, doing what the linear transformation does and spitting out the answer in the basis B again, versus maybe standard to standard or any other basis, whatever the case may be. Right? How are these two related? Well, they're related by the change of basis. If you have standard to standard, versus this one, what are you going to do? You're going to do exactly what we did here, right? You got this linear transformation from standard to B. Act on it via T, which takes elements in B and spits out the answer in B. And then translate B back to standard. Exactly as NJ is suggesting. Exactly that. And this is the inverse of that. So Walid is asking us to explain the order, and let me explain it how I view it. Suppose you've got a very deep mathematical question. So you go see a mathematician and you ask him or her the question in English. Professor works it out and gives you back the answer in English. It's all good. However, sorry, there's one too many here. Too many. However, no English-speaking mathematician is to be found. But you do have somebody who speaks Russian. Unfortunately, your Russian isn't what it should be. So what are you going to do? Well, you have a friend who speaks Russian. So you'll ask your friend the question. He will translate to Russian to the professor. The professor will be asked the question in Russian. Think about the answer. Spit out the answer in Russian. And then your friend will translate back to you. That's going to be the same as having found a professor who speaks English. You ask him the question. He thinks about it and gives you the answer in English. It's going to be the same answer. That's exactly what's happening here. Can the transformation in the middle be between any two ordered bases? And you're absolutely right. It doesn't have to be between two of the same, right? So if you had T going from B to C, this would take standard to B. And this you would need to go from C back to standard. And again, it doesn't even have to be standard versus standard. It could be any two bases there as well. Absolutely. Is this material useful for testable material? And somebody was asking, is this related to diagonalizability? Well, the answer is yes. Yes for both. Jean-Pierre is asking, if we know T from standard to standard, why bother with this? An excellent question. And let's illustrate. I don't. What was the matrix representation for t from standard to standard? I want to say -2, 1, 1, -2. Is that correct? Can anybody? Thank you. Let's diagonalize this matrix. Can we diagonalize? Let's look at the characteristic polynomial, which is the determinant of xi minus a. So x plus 2 minus 1, x plus 2, which is x plus 2 squared minus 1, x squared plus 4x plus 4 minus 1, or x squared plus 4x plus 3, which factors is x plus 3, x plus 1. So you see the roots of the characteristic polynomial. While we're here, let me point out that if the characteristic polynomial factors completely into polynomials of degree 1 into distinct factors, the matrix is diagonalizable, right? Because the eigenspace always has dimension at least 1. So you always, if it factors into distinct factors, it's good enough. If factors had multiplicity, like square and cubed, then you want to make sure that the eigenspace has the same dimension as the multiplicity of the root. But in this case, we're guaranteed. The eigenvalues are going to be -1 and -3. Both minus. -1 and -3. And let's work out the eigenspace associated to -1. Right? This is AV is -1V, right? Or so this is -2x plus y, x minus 2y equals -xy, or when you bring this to the other side, -3x plus y, and x. Something is wrong. What have I done? The minus becomes a plus, so it's just -x, and this is x minus y. Thank you. So -x plus y is equal to 0, or x minus y is equal to 0 if we set up a matrix. And row reduce. Row 2 plus row 1 for row 2, and minus row 1 for row 1. We get 1 minus 1, 0, 0. And so the solution is easily seen to be y equals t, x equals t. In other words, the eigenspace E1, E minus 1 rather, is the space TT. A basis for that? Correct. Correct. You don't need to put the column of zeros as long as you know it's there, though. right? So be careful not to make a mistake when you get to the reduced echelon form, you know it's there. Similarly, for the eigenspace associated to -3, same thing. And what do we get here? -2x plus y, x minus 2y. And when you bring that over, the minus becomes a plus, and we get x plus y and x plus y. So x plus y equal to 0, x plus y equal to 0. And so the eigenspace associated to -3 y is t again, and x is minus t. Well, let's put that, it's best to put it. So eigenspace minus tt. Just a sec, I'll be right back. All right, sorry about that. Well, right, I mean, so Sian is asking if we need to exclude t equals 0. We do not, right? You know that the 0 vector is not an eigenvector, but it is in the eigenspace though. Because the eigenspace itself is a subspace, so the 0 vector better be in there. Now what we're going to do is we're going to give a basis, right? A basis for E1, for E minus 1. Right? I mean, well, what's a basis? Well, it was suggesting 1, 1. Very nice. And a basis for E minus 3. Basis for E minus 3 is? Minus 1, 1. Right? You can prove those? Can you? You can show that it's linear independent and spans E1, E minus 1. And similarly, this is linearly independent and spans E minus 3. In other words, you have a basis of eigenvectors. The basis of R2 of eigenvectors of T. 1, 1 and minus 1, 1. these form a basis of R2, both of which are eigenvectors to the original linear transformation. But what does that mean? What is the deal with these being eigenvectors? Well, it means that A times 1, 1 was minus 1 times 1, 1. And A times minus 1, 1 was minus 3 times minus 1, 1. But this minus 1 times this vector is the vector minus 1, 0 in the basis B, right? It's minus 1 times the first one plus 0 times the second. And this is 0 times the first plus minus 3 times the second. So, well, let me call it T now instead of A. And this vector is the vector 1, 0 in the basis B. And this vector is the vector 0, 1 in the basis B. So you see that the matrix representation for T sending vectors in the basis B, acting on it via T and spitting out vectors in the basis B, is going to have these as columns. A diagonal matrix. And so that's why diagonalization works. If you have, right, I mean this, if you have a change of basis that goes from standard to B, and then the inverse, or B to standard, then this is going to be the representation from standard to standard. Isn't it amazing? It really is. Well, I mean, we're going to end soon, but I mean, I'll have office hours on Tuesday. So, but if you've got questions, you can ask them now before I erase anything. But that's why diagonalization works. Because it's just a representation. This is section 9.1. Right? So that's why diagonalization works, because it's just a representation in a different basis. We do have class on Tuesday. Speaking of which, you know, come on with questions. We're going to do review on Tuesday. We'll answer questions you may have. So perhaps Tuesday would be a good time to ask questions about this as well. Three and six. Where is 3 and 6? 3T. I'm not sure where the 3 and 6 is coming from there. 3t and 6t as the eigenspace, perhaps, then yes. Yes. I think only if you're comfortable with computation of kernel, that should be fine. Yeah, okay, very well. Yeah. But so there it is. So that's the idea. The idea of diagonalization is just a representation. So this shows us the relationship between the two transformation and eigenvalues. Exactly, right? And here we had, what did we have again? This was -2, 1, 1 minus 2. And here, a representation from standard to B, actually B to standard. This is the matrix 1, 1, minus 1, 1, right? Because it takes, again, I never remember, but I can work it out immediately. When you multiply by 1, 0, you get the vector 1, 1. So it sends B to standard. So that's exactly what you want. And this is that. And this is the inverse of that, or perhaps what we should say which is how we introduced diagonalization in class. Or -1, 0, 0, -3 is P inverse AP, where P is that matrix right here. Right? When you bring this to the other side, it's P inverse AP. So let's work it out. The inverse of this, determinant 2. So 1/2, 1, 1, minus 1, 1, A. And this business, let's do the multiplication just to see. It's always nice to work everything out. -2 plus 1, 2 plus 1, and -3. -1 minus 1 is -2. 3 minus 3 is 0. 1 minus 1 is 0. And -3 minus 3 is -6. Or -1, 0, 0, 3, -3. Exactly as expected. So this shows us the relationship between transformations and eigenvalues. Exactly that. It does still show to be counting. Don't worry about it. I'm making it optional. 1/2 is 1 over the determinant. Precisely that. So this ties diagonalization with just a representation in a different basis. Yeah, if you're given a basis, if you're given an ordered basis like we were, I don't know what it was, but I mean maybe this. I suspect it was 3, 1. I write the elements as columns. And this gives me a change of basis matrix. I never know which one though. And you don't have to. You can take a moment and work it out. What happens when you multiply by the vector 1, 0? You get the vector 3, 1. 3, 1, which is the first basis element. So if this was 1, 0 and B, meaning 1 times the first basis element plus 0 times the second one, so really this, it spits out what it is in the standard. So this is the change of basis matrix from B to standard. You never have to remember what it is because you can always work it out. Put your basis elements as columns. It gives you a change of basis. Just figure out which one it is. And let me finish because I have to get going. But let's do the example that was suggested earlier of projection. Suppose you want to project on the vector 1, 2. So vector 1, 2, which is right here, say. And suppose you want to find a matrix representation for this linear transformation. So T of U is projection of U onto V. A linear transformation from R2 to R2. I'll let you prove that's a linear transformation. All we want is Trent, I think I explained it right. Put the basis vectors as columns, and it gives you a change of basis. Right, so projection of U onto V is a linear transformation. Again, I'm letting you prove that. You can prove that from the definition. My question to you is, what is the matrix representation? So what is the matrix representation, I should say? From standard to standard. Well, you can work out what the projection is, how 1, 0 is projected onto V, how 0, 1 is projected onto V, and then you could put them as columns, and that would be that, and it's all good. But we can do it without doing any work, almost. Can we spot eigenvectors? Can we spot eigenvectors? Well, if you take the vector 1, 2 and you project it onto itself, what do you get? If you take the vector 1, 2 and you project it onto itself, right? Because I mean, if you take a vector u and you project, that's what you get, right? You get this business here. But if you take the vector 1, 2 and you project it onto itself, you get the vector 1, 2. So t of 1, 2 is 1, 2. In other words, it's 1 times 1, 2. And what happens if you took a vector perpendicular to 1, 2? If you take a vector perpendicular to 1, 2 and you project it onto 1, 2, you get 0. Exactly. You get the 0 vector. What is a vector perpendicular to 1, 2? Can we spot one just by looking? Is Walid the only student still here? Thank you. Minus 2, 1. Minus 2, 1 is orthogonal to 1, 2, so it gets projected to 0. The 0 vector, or 0 times minus 2, 1. And that's all you need. You're done. In the basis, in the ordered basis of eigen, right? So first of all, 1, 2 is an eigenvector associated to the eigenvalue 1. Minus 2, 1 is an eigenvector associated to the eigenvalue 0. So if you build an ordered basis of these eigenvectors, t from B to B will have a diagonal representation with the eigenvalues on the main diagonal in the order in which they appear as eigenvectors in the basis B. This is an eigenvector corresponding to 1. This is an eigenvector corresponding to 0. 1, 0 on the main diagonal. That is your representation from B to B. And now if you want standard to standard, well, it's going to be B to B, standard to B, and then B to standard. Just a multiplication of matrices. Well, I mean, look, if you got perfect on the midterm and you remember everything, I mean, you'll probably be safe to focus on the second part. Again, to be able to do the second part properly, you need the first half. Look, so Walid doesn't understand how we got this. It's just the eigenvalues on the main diagonal, right? Because t, right, in this order basis, this is t of 1, 0. And it is 1, 0 in the basis B. And this is t of 0, 1 in the basis B. And it is 0. Well, in fact, it's 0, 0. So it's just these things as columns. How are we doing? Let me just end by noting that what are we really saying? If you have a linear transformation from Rn to Rm, it's multiplication by a matrix. And multiplication by a matrix is a linear transformation, so they're equivalent reformulations. What if you're going from a finite dimensional vector space to another finite dimensional vector space? This idea of change of basis extends to that as well. Right? If you're looking at P2, let's say, which is the set of polynomials of degree less than or equal to 2, you can give an ordered basis, maybe x squared, x and 1, and consequently, every element has the representation a times this plus b times that plus c times that, or a, b, c in the basis b. So we convinced ourselves that linear transformations from Rn to Rm were really multiplication by a matrix. And now you can extend that immediately to linear transformations from finite dimensional vector spaces to other finite dimensional vector spaces. These are all multiplication by a matrix in exactly the same way. Case in point, perhaps, the derivative. Let's take one example and we'll end with that. The derivative. For those of you taking calculus, or for those of you who have done calculus, you know that the derivative is linear. The derivative of a sum is the sum of the derivatives. The derivative of a constant times a function is just the constant times the derivative of the function. The derivative is a linear transformation. So the derivative should have a matrix representation viewed as going from P2 to P2. You know the derivative of x squared. What is the derivative of x squared? Derivative of x squared is 2x. Absolutely. So x squared, if it's viewed as the vector 1, 0, 0 in your basis B, the derivative, how important is this class to multivariable calculus? It's quite important, I would say, for 222. I mean, you don't need to know every single thing, but lines and planes in 3D for sure, and Kramer's rule comes up quite a bit. Let's rewrite the vector 2x in the basis B. What is the representation of 2x in the basis B? And we'll do the same for the other ones. Very nice. 0, 2, 0. Derivative of x is? Derivative of x is 1, as you know. So that is the vector 0, 0, 1 in the basis b. And the derivative of 1 is 0, which is 0, 0, 0 in the basis b. So your derivative, your linear transformation, viewed as going from the basis b to the basis b, has matrix representation, these things, as columns. 0, 2, 0, 0, 0, 1, 0, 0, 0. There it is. This is the matrix representation viewed as going from the basis b to the basis b of the derivative transformation. How are we doing? Post-midterm. The final exam concentrates on post-midterm material. How do we generalize it to P2? What do you mean? Well, I mean, that's what I thought. I was generalizing to P2. Can we find a matrix representation for the derivative for all elements in P2? Well, I mean, all elements, right, are going to have the form ABC now. So if you multiply this by ABC, which is the derivative of ax squared plus bx plus c, you know the answer is going to be, right, the derivative of ax squared plus bx plus c, you know the derivative is going to be 2ax plus b. And observe, when you multiply this out, a row of 0, so you get a 0 here, 2a and 1b, this is in your basis b, which means 0 times the first basis element plus 2a times the second basis element plus b times the third basis element. Exactly as you knew. But there it is. All right, folks, thank you all for sticking to the end. I will see you on Tuesday. Come armed with questions, and we'll take it from there. I'll post this. I'll post this on my courses. I'll have office hours pretty much all week. I'll send an email giving you my office hours for the week. All right. You guys have a good rest of the day, and I'll see you on Tuesday. Have a good one. I'm not teaching 140 this semester. I am teaching 141 in the winter, though.